Right, so having cleaned up my slides, well, I'm still not sure I've cleaned them up. Right, I'll start from here. Okay, so storage manager lives in that part of the database system. Alright, so a couple of things about storage technology which obviously impact a lot of the stuff that we'll be doing later. So persistent storage, typically disk devices. Disk devices are large, they're relatively cheap for the amount of bytes you get on them, but they're also relatively slow. Okay, so we use them. Oh, and the other important aspect is if you want to access data off a disk, you've got to read in a whole block of data. You can't say, hey, I just want this byte on the disk. You've got to read the block that contains that byte, and then you can access the byte. So you can use them for long-term storage. The other thing is when you turn the power off, they don't go away, which is a useful thing. On the other hand, so that's storing data. As soon as you want to manipulate data in any way, you've got to get it into memory. Memory is small, expensive, but blindingly fast, and can be accessed at the individual byte level. So once you've got a block of data from the disk, you can do stuff to that block of data really quickly, and a lot quicker than the relative cost, or relative to the cost of reading in that block of data in the first place, which is what point this is meant to make. Okay, so the cost of doing something with a disk is, that's probably a bit over exaggerated. It's probably more nowadays, probably more like 10 milliseconds, but still a hell of a lot slower than what it's going to cost to compare the fields into tuples in memory. So when we want to analyze how much things cost, and a lot of the stuff we do in this course is, here's an algorithm for implementing join. How much does it cost to implement that algorithm relative to this other algorithm that implements join? So the important aspects of cost calculations are that we always deal in whole pages. The cost of doing stuff in memory is irrelevant. Maybe that's not a great assumption, but I reckon most of the time it would be reasonable relative to the cost of reading in a block. And so the overall cost of all of these database operations is basically how many pages of data do you have to read or write. That's going to be the overall determining factor of the cost. Now, to do that kind of analysis, you're making certain assumptions, and one of them is that every time you want to access a page, you actually read it in or write it out. But of course, we've got a buffer pool sitting in between. So a lot of the time, you might access a page, but that's going to a buffer that's already in memory. So it's a page access, but it's not costing I/O. The other complicating factor with determining costs is you're reading in a page of data. How many tuples does it contain? Especially if the tuples are variable size. Don't know. And in particular, how to work out how many pages there are in the relation. If you know that if all the tuples are the same size, then you can work out how many tuples fit in a page, and then you can work out the total number of pages in the relation. But if the tuples are variable size, then it's a bit harder to work that out. So often we'll just say, we'll pick an average tuple size and assume that's going to be a good basis for working out how many tuples per page, and therefore how many pages. Okay, so right at the bottom level, we've got a file manager that basically understands if I ask for data from a certain relation, then the data for that relation lives in a particular file. What kind of operations do we have to deal with at this level? Well, basically we're dealing with the file system. So we're opening files, we're closing files, we're reading from them, we're writing to them, we're moving around in the files using the seek operation, and very occasionally we want to force the contents of a particular chunk of memory onto the disk. That operation you'd probably want to minimize to keep things efficient. But basically these kind of operations are what we're doing. And they're all the Unix versions of those operations. Other operating systems will have a different set of file operations. Alright, well last time I mentioned how data was stored in a system, and some databases might use a single file, some databases like Postgres use multiple files for storing the data. So if we actually had a single file database, and it's not so impossible, SQLite is a good example, the entire database is stored in one file. So how do we arrange the stuff in that file? Well, one thing to keep in mind is that tables are going to change over time, and we might start out where a table occupies 2 pages, but we add more and more tuples to it and it occupies 20 pages. And similarly, all the other tables might be like that. So we might end up with all of the table data interleaved in memory. But an example of how we might arrange a single file, we might put a bunch of parameters at the start, which might contain things like the total size of, well, the total amount of file space that we're willing to allocate. Maybe we want to put a limit on that. Might contain the size of data blocks. We might necessarily want to use the natural size of the file that the file system provides. We might want to take 2, 3, 4 file system blocks. Then we might have the catalog information. Of course, we create the catalog data initially. We might add some tables subsequently, but in the meantime, we've put a whole lot of other stuff into the file, and we might have to continue the catalog further up the file. Similarly, if we create a table initially and we start filling it up with tuples, eventually we might create another table and put tuples there, and then we come back to create more tuples in table 1. They have to go somewhere else. We can't necessarily just push everything up and make room, so we're highly likely to have the data for particular tables spread across the data file. Other thing to consider, if we remove an object, so if we drop a table totally, it occupies a certain amount of space. So maybe if we drop table 1, we've got table 1 data, we've got an index for table 1, which maybe was added later after the table was created, and then we've got another chunk of data for table 1. So all of this space is now effectively free, and we can reuse it for other objects. So if we subsequently create table 3, we can store that. We can start table 3 off here. But clearly, having this stuff scattered throughout the file, we need some way of being able to say, all right, if I'm looking for the second page in table 1, is it in this chunk or is it in this chunk of data? And so there's going to be some kind of mapping table that tells us that information. So as far as allocating space, on Unix or Linux, if you want to extend a file, you can simply seek to wherever you want to seek to, even if it's way beyond the end of the file, and then you can write data there. Interestingly, Unix doesn't fill up the disk with all the intervening space until you actually make use of it. So particularly you can have quite a sparse file, which conceptually is very large but doesn't occupy a lot of space on the disk. So if you've got something like that, then it's relatively easy to implement a disk/file manager. So if you know, all right, I need to allocate some more space, I've got, if we go back to this diagram, let's say I've got the data for table 1, I want to create a new table, table 2. If I wanted to, I could say, all right, table 1 might grow a bit larger, so I'll leave a large amount of space there and I'll start table 2 up here. And so if you just seek to where you want table 2 to start and you start writing tuple data at that point. So that leaves space for table 1 to grow into. But as I mentioned before, if table 1 eventually bumps into table 2, you can't keep writing, you've got to put the rest of table 1 somewhere else. So you can allocate more space in the file and start writing table 1 data there. So a simple bunch of abstract data structures for implementing a setup like this. So a database descriptor, which kind of corresponds to that open DB thing that I mentioned before, could contain the name of the database, the open database file. There's only one file in this setup, and typically there'd be some tables that described how the space is laid out within the file. And similarly, we need some kind of catalogue data to map names to positions in the file, so you'd have something like that as well. If you open up a relation within that file, then all right, we want to know its name. We also want to know where it starts in the file, so where either is the first page of data, or maybe there's an initial header page which contains information about the table. And also we might be interested in knowing the number of pages of table data. So this, to some extent, is assuming that we allocate enough space for a table that that's all we ever do, and then we can store tuples in it and we never overflow it. So that setup would work quite nicely for a scenario like that. Right, so under that, if we want to start using a database, we ask to open it and we give its name. In the case of SQLite, that'll be a file with maybe a .db suffix. We can then make a copy of the database name. We can open the relevant file, grab the file descriptor, and from that file descriptor, potentially we can read a space table and a name table, which, if we look back at that original diagram, wow, what am I doing? I'm going forward, not backwards. All of that information might be stored up here in the catalogue location. So the free space table, or where we find stuff in the database, and where particular named objects are located in the database might be stored up there, but we read them into the data structure that represents the open database. And to close the database, just interesting. So here we're assuming, and the other assumption we're making here pretty much is that it's a single user database. So a user opens it up, makes a whole lot of manipulations to the database, including changing the space table, changing the name table, and when we eventually close the database, all that data has to be written out to disk again. Now you might want to structure things differently so that as soon as you make a change, then all that data gets flushed to disk to make sure it's always synchronized. But if we've only got one person using the database, we don't need to worry about that. Right, if we want to open a relation, we know the name of the relation, we know the database that it's located in, which we've already opened. So we can make a relation descriptor, make a copy of the relation name, get some information from the mapping tables about where the relation starts and how many pages it contains. And then to close it, we simply free up the relation object. So these objects, things like relations and databases, we're going to have a look in a few minutes about how Postgres implements them, but for the time being we'll just take this simple abstract approach to the structure. Right, if we want to get a page, then in theory we can use the page mapping table. So we're given a page ID. What we need to work out whereabouts in the single database file this page is located. We can use the map table to work out the offset in the file, then we can seek straight to that location and then read the page into a buffer. So what does the buffer look like? Well, it's just a big chunk of memory, and what it's going to hold is tuples in some kind of format, which we need to read the catalogue information to know how to interpret, the format of bytes in the page, and also potentially some kind of mapping within page mapping table. But that's what we read into the buffer. And if we want to write a buffer that we've made some changes to, then we can do it like that. So ultimately, the page offset function has to give us an absolute offset within the file. But of course we get to it through a page ID value. And like I said, we're going to have to potentially, if we know that all pages are exactly the same size, we can compute a page offset simply by multiplying the page number by the page size. But if we don't know that, or if we don't know that the pages are necessarily going to be laid out sequentially, then we'll have to go through some kind of mapping table to get there. Right, so if at some point we decide, hey, we need to allocate more space, then we might write a function called allocate pages, which seeks beyond the end of the file, or seeks to the end of the file, sorry, and then adds more space after that, and adds a new entry into the space map to say, all right, this new page that we've just allocated lives at this particular location in the file. And if we want to get rid of pages, all we can really do is mark them as no longer being used. And eventually, perhaps the allocate pages function could take account of that and say, all right, if we need a new page and there's a free page available somewhere in the middle of the file, then we can use that. So if I wanted to scan through a table, then this is how I can do it. What's interesting about this is that we've got a buffer somewhere, so we explicitly allocating the buffer. In the case of Postgres, there'll be a whole pool of buffers already allocated, so we can use that buffer pool without having to allocate anything. Scan through the pages of the file, so I want page 1, or page 0, page 1, page 2, page 3, up to the total number of pages. Then get the appropriate page, and then typically what we're going to do, once we've got a page of data, we're going to scan through that page and look at all the tuples in that page. Alright, so let's do a back of the envelope calculation for how much it might cost to scan a particular relation. So imagine we've got 100,000 tuples of this type in a relation. The average size of those tuples is 200 bytes. So perhaps X, Y, and Z are all fixed size chunks. So we know for sure that every tuple is 200 bytes long. How big are the data pages that we're going to be dealing with? They're 4K. How much time does it cost to read a data page? How much time does it cost to check a single tuple? How much time does it cost to form a result tuple? And how much time does it cost to write a result page? So imagine that we're computing a whole lot of tuples and we have to store them somewhere at the end. All right, so total time cost for doing this query here, assuming we don't have any indexes and assuming that the tuples aren't ordered in any way. Okay, so clearly what has to happen is we have to read page by page by page through the relation, then tuple by tuple by tuple, check whether each tuple satisfies that condition, and we're told that 50% of the tuples are going to satisfy the conditions. So let's take a look. Okay, I hope that's consistent. Forget about that one. Alright, so how much is it going to cost? Well, first thing we need to work out how many pages do we have to read, and remember I said that was going to be the dominating cost. So if there's 200 tuples per page and 100,000 tuples, then I'm going to have 5,000 pages. I hope, is that right, or is it 500? Quick, fix my arithmetic. 5,000 or 500?
500.
Good. So straight up we know that if we've got to read 500 pages, then total cost for doing that's 500 times 10 milliseconds, which is a fair few seconds actually. Interesting. And that's why we have buffers, so we don't have to read them all every time. Alright, so given a page, how much is it going to cost to process a page? So we have to scan through all the tuples in the page, and in fact, and check each tuple. So forget about that 40 microseconds that I had up before. Scanning the tuples doesn't cost any time, but checking each tuple costs 1 microsecond. So there's 200 tuples in a page. So for each page, each page 200 tuples and 1 check, 200 microseconds multiplied by 500. So that's a few microseconds. In fact, it's 100,000 microseconds, which is 0.1 of a second. If I got that right. And that's for the whole file. Okay? So there's not a lot of time cost involved in checking all of the tuples. Forming result tuples, 1 millisecond, so we know we were told that only half the tuples match, so we only have to form 50,000 result tuples. Cost of forming 1 result tuple is 1 microsecond, so let's see, call it make tuple cost. 50,000 times by 50,000 microseconds, which is even less than that. Is that amount of time for the whole file. So you can see that, and you can argue with my numbers, my assumptions about how much things cost, but the cost here is a lot less than the overall cost here. Now, let me see. So that's 5 seconds. Okay, so the reading time is total of 5 seconds. All of the processing time for all of those tuples is 0.15 seconds. So it's a lot less, put it like that. So the dominating cost is generally going to be the I/O cost.
Why when we are given the size of the page 4096? I think 200 was actually the size of the tuple.
Oh, really? Oh, God. So then it's all wrong. Yeah. Good point. Thank you. Too late. I have to go back and recalculate. You're absolutely right. I should have determined the number of tuples per page. In fact, all right, if we do that, I think the I/O cost is going to be a lot higher, because we're not going to have 200 tuples per page. We're only going to have 20. So I/O cost blows out massively compared to the cost of doing the checking and forming the tuples. Now, of course, there's another I/O cost involved. We've got to write the results as well. And so if we go back to the assumption that there are 200 tuples per page and we're forming 50,000 result tuples, then that's a few pages that also have to be written. Why didn't you point that out earlier?
It doesn't change the nature of the calculation.
Yeah, right. It would make that a lot more. So a number of pages written. Once again, so that's the number of pages written, and you multiply by 10 milliseconds. So that's assuming that we've got 200 tuples per page, which we know we don't. All right. So anyway, point is that in future, when we do cost models, we're going to ignore what happens in memory, and we're just going to talk about pages read and written. All right, so looking at Postgres, wow, this diagram don't quite fit, but I showed you this diagram last time. So under the PG data directory, there's a subdirectory called base, and under the subdirectory called base there's a whole lot of other subdirectories, each one of which represents a database, and under each database directory there's a whole bunch of files that represent the individual tables, plus other auxiliary information associated with the tables. There's also a bunch of tables represented under a directory called global, and that's all of the catalogue tables that are relevant to the whole system, which in Postgres is called a cluster. So the actual PG underscore database table is obviously going to live there. The users table is going to live there, but the individual catalogue tables for the individual databases are going to live down here. And there's a bunch of other directories as well, but this is a critical one because that's where the actual data that we need to manipulate lives. Alright, so the Postgres Storage Manager has a bunch of data abstractions, somewhat like the ones that I've just been talking about. And so one thing that we have to do, map from relation names to files. So there's a notion of a relation file node to do that. When we open a relation, if we are running an access method that has to keep opening the relation and keep accessing the relation, we don't particularly want to keep reopening the file all the time. So we keep a pool of open relations, and similarly we keep a pool of open file descriptors, so we don't have, so you know, apart from opening relations, we don't have to keep reopening files that we opened earlier. We keep them hanging around. There's two kinds of files in a Postgres system under one of the database directories. There's files called heap files, which aren't anything like the heap data structure you might have seen in your data structures course. It's basically just a file of pages, and in each page there's a bunch of tuples. And there's also index files which have quite a different structure, basically a key value and an offset. Postgres has this notion that there might be different kinds of storage devices. So it's got this abstraction for the storage manager, thinking that maybe once upon a time we might use tapes to store the database, or we might store them on hard disks, or we might store them on optical disks, things like that. So there's an abstraction layer to handle all the different kinds of devices, but basically it doesn't get used nowadays. It's basically just disks. Okay, so for Postgres to open a particular relation, or to access the data for a particular relation, it needs to have the name of the file, and it gets that information by storing a triple in a relation file node object. And all of these values are object identifier values, so they're just numbers. So there's the number that represents the namespace or the schema, number that represents the database, and the number that represents the relation. So all of those values can be extracted from the PG underscore, the various PG underscore tables. So I think you can see, looking back at that diagram of the structure of the files in Postgres, once I've got the space node, once I've got the DB node, I've got access to the appropriate directory. Within that directory, once I've got the OID for the relation, I've got access to that. And table space doesn't seem to appear in opening the files. All right. So I mentioned that some of the tables are global, things like database and users. And that's where the namespace node comes in. So we want to know whether, let's just back up here to this diagram, we want to know whether the table data lives under this directory or whether it lives under this directory. And so we can work that out from there. And the DB node value for that is 0 because we're not interested. Alright, so here's a piece of code actually extracted from Postgres, and basically what it does is it takes one of these relation file node objects and works out what's the name of the actual file for that table. First thing it does, malloc some space. I don't know where enough space comes from, I think I made that up, but allocate a buffer that we can use to hold the file name. Then we check whether it's one of the global tables, and if it is, we're expecting the DB node to be 0. Notice we've got an assert with a capital A. That is not the regular Unix assert, it's the special assert that Postgres uses to handle errors. If it is one of these tables, then basically we go to the name of the data directory, which is basically your PG data value, and the global directory and the OID of the relation within that directory, and we form a file name doing that. Otherwise, all right. I'll talk about the table space in a minute. If the table space is just a normal table space, which is basically where all of the data tables live, then how do we work out the file name? Well, we get it from the PG data directory /base/database OID, which is going to be the name of the directory, / relation ID, which is going to be the name of the relevant file. And so all of that together gives us a file name that we can use to open the table and start accessing the data. And Postgres also has the idea that you might want to put tables in different locations if you wanted to spread the load on. If you've got a whole lot of tables and you want to spread the load on the disks themselves, you might want to put the tables on different file systems. So that's a way of doing that, and that's where the table space ID comes into play. All right, so that function there will take some information about a relation and generate a file name to open the data for that relation. So I mentioned before that Postgres has a file descriptor pool. Why does it need that? A couple of reasons. Unix has limits on the number of files that a given process can have open at any one time. So we can't open more than, I forget what the number is these days. It used to be 32, but it seems to be a bit larger nowadays. But the other reason why we wanted a pool of open file descriptors is that you might work out, while you're executing a particular relational algebra operation, you might be required to open a number of different files. So if you're doing a join that involves 20 tables, which is not infeasible, you might need to open the relations files for all of those 20 files all at the same time. And there might be temporary files involved as well if you're doing a join that big. And it's possible that you might bump into the Unix open file descriptor limit. So we have a pool of file descriptors which is larger than the Unix pool, and we can keep an entry for a file that used to be open, but we might have to close it down because we've run out of file descriptors. The other reason for doing this is that if we don't want to keep opening files if we don't need to, because an open file operation is relatively expensive. If we keep the file open, then basically what we can do is if we generate a rel path like this, then we can look up in the file descriptor pool and say, hey, this file descriptor is already open, I don't need to open it again. Or if there's an entry there and we see that file descriptor is closed, then we have to choose another file descriptor in the pool to close down and open and store it in that entry in the file descriptor pool. So the open file data structure that Postgres uses is simply an integer which is an index into this table of virtual file descriptors, if you like. So these are the functions that Postgres uses. So they're kind of analogous to the Unix functions to open files, close files, seek, and so on. But rather than working directly on file descriptors, on Unix file descriptors, they work on virtual file descriptors, which are indexes into this pool of file descriptors. And the pool of file descriptors is basically stored in an array. The array is dynamically allocated, and all of these open file descriptors contain a real file descriptor, unless it happens to have been closed, plus a position, a current position in the file. And they're also linked together as well to facilitate searching in the array. So whenever you do something with a file inside Postgres, you've got a file value, which is an index into this table. And so that's what you do. So you go to this table, you get the relevant file descriptor value, and if you want to go straight to the current position in the file, you've also got that information there. So Postgres doesn't have to deal directly with file descriptors, or the higher levels of the system don't have to deal directly with file descriptors. They deal with these virtual file descriptors. And that's what a VFD record looks like. Let's see. Oh yeah, so the linked list of virtual file descriptors is basically to work out what's been used recently, what hasn't been used recently, and therefore find candidates that are potentially closable if we run out of open file descriptors while we're executing a query. What else is interesting in here? So current logical file position, the name of the file that was used to open that. So if a file descriptor happens to be closed, as we see, there's a special value for that. And we need to access something in the file. We've got the file name here. We can reopen the file descriptor after closing down one of the other file descriptors. And I think that would be a good place to stop. All right, so next time we'll talk about the file manager and get on to how tuples are represented, how pages are represented, and so on.